This is a Raspberry Pi Pico, pretty standard, and I've been using these in the transputer emulator. Now the transputer has 2K of onboard RAM, which is way less than this, but when used in a TRAM module, they sort of have around about 2 megabytes of RAM. Now that's more than the Pico's got. The Pico's only got about 230 something K. It's got 2 meg of flash in that chip there, but the RAM that's built in is only about 200 and something K. So that's quite a long way short of 2 megabytes. So in order to just make sure I can run transputer code on a fairly standard RAM configuration, I thought it'd be an idea to have a go at putting more RAM on here. Now it's quite easy putting flash on. You just change that chip for a bigger one. There's 2 meg of flash and you can go up to 16 meg, I think. So what I did for the RAM was a similar idea, and that's use SPI RAM. So I made a little PCB there. It's not really a hat, it's more like a sort of little pair of underpants or something. But on there's space for a SPI flash in the SO8 package, a couple of jumpers, so they disconnect the signals from the flash chip. There's 3 jumpers there actually, and actually no, that's a capacitor, so there's a bit of decoupling on the board. So if you don't want to use it, you can just leave those blank, and you can use some of the lines as GPIOs instead of having to drive the SPI flash. And it's got the same sort of castellations, it just sits there. Unfortunately I made a little bit of a mistake in that if you've got the programming pins soldered, you've got to raise it up a little bit to put it up above the top of those jumper pins. But anyway, the board when it's built up looks like that. So that's the PCB sitting there. And this is a 64 megabit SPI flash, so that's 8 megabytes of RAM, so that should be enough. The code, so the lines that are attached to the SPI RAM are on SPI1 on the Pico. The Pico's got a couple of SPI, hardware SPI ports, and of course you could use the PIOs if you wanted to have some sort of soft SPI port, but these are on the SPI1 pins, so that's quite easy to drive from the SDK. You've got some functions to drive the SPI. Now on the internet there is some code to actually take a chip like this and use the page faults within the processor to actually effectively map it into the memory space of the RP2040. The SPI flash has got its own dedicated execute in place flash SPI driver, so that flash memory does appear directly using hardware in the address space of the RP2040. The SPI1 interface can't do that, but you can, using this code, and I haven't tried it, you can use code which will use page faults to actually map the SPI RAM into the address space of the RP2040. It's a bit slower obviously because you've got code running for every access, but you can actually do it, and then you should be able to run code fairly unchanged, just accessing memory, and it comes from here instead of the internal RAM. Now for me, I didn't do that because I'm using an emulator here. I've got access to the memory store and load code. It's code anyway, so I thought I'd just add it to the emulator, so that's what I've done here. So this isn't running page fault code, it's just running SPI accesses every time I access the memory. So instead of doing an array read or write, I do an SPI read or write, and it's fairly fast. I mean the whole thing's pretty slow anyway, and it doesn't seem to make a vast amount of difference, but it does give me more RAM, so I do stand a chance of running stuff that requires 2 meg of RAM, whereas with the 230 odd K there's not really much chance of doing that. So yeah, it all works. once it's soldered on. This, I have got the programming pins underneath there on the header, so it is, yeah, you can just about see that, it's up off the board by a millimetre or two, which doesn't really make much difference. And I've soldered the jumpers across. You have to run the 3.3 volts down on a wire because it's not available on the pins down here where SPI1 lives. And this is the best place, obviously, to put something, because you've got a flat area of board here that you can just plonk that on top of like that. And I've put nothing on the back. I don't want it to short out to test pins or anything if you do lie it flat. If you're using wires or something for programming, you could put it absolutely flat on the board, which would be, well, just the height of a PCB. This is a 1mm thick PCB, not 1.6, plus the SO8. That's pretty small. So yeah, I can run that. I've tested it. I wrote a little memory test and it seems to work, and I can run code out of it. So we'll have a look at that. I've got the Pico transputer emulator here. I've got the Arduino Mega, and the LED there will actually show traffic going over the link to the laptop. And I've got the little Pico with the 8 meg underpants there, and the Pico probe for programming. So in these two windows I've got the USB serial output over here on the left, and this is a terminal which has got some example code. So what I'm going to run is prime.btl, which is a prime number generating code. So the Picoputer at the moment is set up to have just 32 bytes of internal memory, which is coming from the Pico's internal RAM. And I think there's 256 bytes or so, 256k of SPI RAM coming out of the 8 meg SPI RAM chip sitting there. So just to show that it works, I'm going to run the prime.btl, and I'm sending it down using my Arduino link server. So over on the left hand side I've got the USB serial output from the Picoputer, and on the right hand side I'm going to run some example code. This is a prime number generator, prime.btl. So if I run that, that's now sending the code over the link. This is the second stage bootloader. So the first stage is only ever 256 bytes maximum. Well, it's yeah, there's some numbers of bytes that you can't actually download, but there's up to 255 bytes. So now it's asking me to type a number, so this is the highest number that it wants to actually check for primes. And there's some debug messages on the left hand side over here. I've taken quite a few of those out at the moment, compiled them out to get a bit more speed and a clearer screen. So if I type 500, it'll look for primes up to 500. So you can see it's running fairly fast. We've got an instruction counter over here. There are 100,000 instructions. So there's over 100,000 instructions per second at the moment going out to SPI RAM. And there you go, there's 1.3 million instructions to run that. And that is external SPI on that little board there. So I can go, if I come out of there and I'm going to reset, just pull the power out. If I go here, we do have some other demos. We've got the Minix demo, which is loading the operating system. So Minix is a small Unix-like operating system that came quite a while before Linux actually. And you just need to load boot.btl. Now this doesn't work, unfortunately. It doesn't get all the way through, and I don't know why at the moment. But if we run that, that's the first stage bootloader. So the second stage is now running, and that runs for a while. That then loads up a secondary bootloader for Minix, which sizes the memory, and the secondary bootloader, bootstrap loader, is actually the third, because there's a small 255 byte one, then the bootloader for Minix, and then the secondary bootloader. So it's done quite well to get this far. 500,000 instructions at the moment. And there you go, you can see it's found 80800 bytes of memory. So that's the internal and the external RAM. So, and it's now loading the boot monitor, which takes a while. You can see there's traffic going on. We've got the red lights over here actually doing something. And there we go, so that's now in the boot monitor, so you can use this as an interactive terminal. So you type help and out comes the help message. Pretty slow. I think that's probably due to my inefficient link protocol more than anything else. It does seem to be running fairly quickly internally. If I do boot it, then it does load one module, the kernel module, but then it stops once it's done that, and I don't know why. Don't know why this isn't working. But obviously this is using quite a lot of the external SPI RAM, and seems to be working fine. I'll let that run on because it takes quite a while. I'll speed it up here. And there you can see the activity stopped over on the link to the host, and it's saying loaded from 8 blah blah 9D0 to 8 blah blah EC70. It just stops at this point, and I've not seen it give any output. I don't really know why. I think I'm going to have to implement some of the peek and poke stuff and then run this on the emulator on the PC, which does work, and see what differences we get. There's a few warnings here which are a bit strange, but I don't think that's the problem, because I'm running the same code here as I run in the full PC emulator. The full PC emulator works, but this doesn't, so I don't think that's anything to do with the problem. It might be some sort of RAM corruption, but I don't think so. I think too much of the code is actually run over here to get through these bootloaders and into the monitor and so on, for there to be any major RAM problems with the SPI RAM. But there we go, that's now got the capability of 8 megabytes if I decide to use it.